So in this video, we're going to learn how to reduce the data that we've acquired on the new ICPMS. So for doing that, here on the screen, I have 3 files that we're going to use. So we have the new PM HCalc macro, that is the reduction program. We have one of these data files that is being produced as we analyze the sample. And we have a folder that right now is empty. But what we want to do first is just take whatever file that you want to reduce and then just throw it in that folder. And the important part here is that the data file is by itself in the folder, because then the macro is going to call that folder and is going to extract everything that is in there. So if you have several files, several of them are going to be extracted at the same time. So you only want one file at the time. Okay, so once you have your file that is isolated in the folder, you want to open new PM HCalc. And a couple things to point out here are, first of all, you want to make sure that you have Excel 2003, and that's important because the macros that are coded in here do not work with newer versions of Excel. The second thing is that you want to make sure that you have isoplot installed, and that's a different topic that we'll cover in a different video. So okay, once you have your a fresh new version of new PM HCalc that is open, and you have your file isolated in a folder, first thing that you want to do is just copy the path to that folder, right? And then go over to new PM HCalc and paste that into cell D1. So what that's going to do is going to tell the macro where your data is, and then it's going to direct the reduction routine to extract all the data that is in that folder. So you want to hit return and then click on import. So what the program is doing right now is that it's going down that txt file, going spot by spot, and is doing the down pit fractionation correction of each one of these points by performing a least squares regression through the acquired data. So once it's done, it's going to take about 30 seconds for the detrital sample to import all the 100 and something spots that you've analyzed. And the next important step here is that when you run your sample, remember that you analyzed a few standards at the beginning, typically 5 or a couple more than that. Then you analyze the standard every 5 unknowns, and then you analyze another block of standards at the end. So what's important here is that you tell new PM HCalc what standard did you use. And in this case, for the most part, we always use SL. So you go to cell B1 and make sure that you have SL typed in here. And then what the macro is going to do when you click on order here in a second is going to go down column A, looking into each one of these names, and then all of those that have an SL are going to be replaced by standard. So let's do that. Hit order. Okay, great. So now all the standards were identified. So now if you go to column U and column W, it's going to show in red the ages for the standards, 6-8 age in the U column and 6-7 age in the W column. So the next important step is that we want to see how those standards behave throughout the run. If they were stable, if there are any mislabeling issues on the standards. So for doing that, we go to this tab down here, the 206-238 tab, and this is going to show us here in the x-axis the number of analysis. So remember, you analyzed 100 unknowns plus a few standards, so it's something close to 140. And then here in the y-axis is going to show you the 206-238 fractionation factor. So what we want to see is sometimes this fractionation factor is going to be around 1, sometimes it's going to be around 0.95 or 0.9. But more important than the absolute fractionation factor is that fractionation is relatively stable throughout the entire run, because that's what's going to, result in good data at the end. So to understand this plot a little bit better, each one of the blue points is one of the standards. The thick pink line that's here in the middle represents the average or the mean of the fractionation value as calculated from the neighboring 6 standards. Then that thick line is going to be, it has an envelope, has 2 thin lines at either side, and those represent the 2 sigma standard error of that measured fractionation value. And then these vertical gray bars are just going to be a 2%, constant 2% uncertainty on that mean. So for the most part, what we want to see is that all our standards, or most of our standards, are within that 2% deviation from the mean value. So as you can see from this file, there are a couple of those that lay outside, so that's what we're going to check first before we continue on with the reduction. And one important thing to note is that because this SL standard that we're using is a natural standard, then some areas of the grain have been affected by natural lead loss, right? So when you have a fractionation factor that has a higher number or a higher value than 1, then it means that it has a younger age and potentially could be affected by lead loss if it significantly deviates from the fractionation that you've measured throughout your run. So we're going to check at least 2 of these standards for now, just to just do an example. So point number 3 is going to be one of the standards that we want to check, and the other one is point number 28. So if you go to sheet 1, those standards that have those high fractionation values here in the U column are going to appear as standards that have a different age that is significantly younger than the average age that you've measured. So in this case, this is grain number 3 that has an age of 542, and then if you go back over here to 206 to 38, this one over here, point number 28, if you go back to sheet 1, point number 28 is down here, and it has an age of 532. So that age is considerably younger than the average age that you measured. And if you look at the W column, where you have the 206, 207 age, that one is significantly younger too. And what this is telling us is that it is very likely that this standard does have some issues, or this particular crystal that we mounted, because this 6-7 age should be way more stable than the 6-8 age throughout the run. And just so you can see that visually, if you go to the 206, 207 tab down here, and then 206, 207 is usually way more stable because we don't have any inter-element fractionation effects during ICPMS measurements of the lead ratios. So you see that there are 2, probably 3 with this one, 3 standards that have a significantly different or noticeably different 206, 207 ratio. Okay, so in order to get rid of those standards and not use them for our reduction, you want to just place the cursor on top, and then you'll see it's point number 3 over here. Put the cursor on top, point number 28, so you make a note of that. Go to sheet 1, and then you start counting for the point number 3. Remember, starting in the row number 3, so it's going to be row number 5. So 1, 2, and 3. Over here, if you take a look at this standard, then this is the young one. Has an age, 6-8 age of 542, 6-7 age of 530. So if I want to exclude that from my corrections, then you'll go to the A column where the name of the standard is, and then you'll type a lowercase xx label in there. So you see that when you hit order, that line is going to turn blue. So lines that are blue are problematic lines in some regard that we'll cover a little bit later in this video. So then the next one was number 28. So if you count from number 3, then plus 28 is going to be cell number 30. So if you go down here to cell number 30, in fact, this is the other one that has an anomalously young age, and again, lowercase x. You hit order, that one's turning blue again. And if you go to the 6-8 tab, you'll see that those standards are not in there anymore. And then our 2 sigma uncertainty envelope on that mean systematic fractionation factor. So when you go back to the 206 to 38 tab, you'll see that in fact those standards are not in there anymore. And then the uncertainty envelope that is around that mean fractionation factor is way smaller now. Okay, let's look at the 206, 207. So those 2 at the beginning are that were off are not in there anymore. And then this one looks marginal, but on the 6-8 ratio, it doesn't look as clear as an outlier as the other were. So we're going to leave it in there for the time being. Okay, so now we got to the point where you've already imported your data. You've looked through all the standards just to make sure that you're using what you want to use. And now what we're going to do is we're going to go through this top bar, all the yellow columns, and we're going to see what some of these filters are and how they work. We've already used cells B1 and C1 that are just telling the program, the reduction macro, what the standard is that you're using. We've already used D1, that is just the cell that contains the folder path where the reduction is going to be directed. And now we're going to look at all these others. So as I told you before, once you click XX here, or you type XX in the labeling of an individual grain, this line is going to turn blue, right? And because there's a filter in the macro that is telling the program that if there's anything here labeled XXX, it's going to turn blue. And there's also something, if you look at analysis number 4 down here, that the whole line is blue. And that is because we have some thresholds that are being applied to the data to just filter or highlight the problematic individual analysis. Okay, so the first filter we're going to take a look at is this 204 counts per second. And what this filter is doing is if you have any significant 204 lead in a grain that is not radiogenic lead and thus represents grains that have significantly higher initial lead concentration or common lead. So we want to highlight those and be careful when including grains that have a significantly higher common lead correction. So we just normally have this threshold set to 600 counts per second. That's going to the ion multiplier. So 600 counts per second or 1,000 counts per second. And you can see down here, if you look at column D, that these values are usually pretty low. So in most zircons, and especially if you look at your Sri Lanka standards, you'll see that they average 10, 20, and for the most part they stay pretty low also in the unknowns. But then every now and then there are some grains that have a significantly higher 204 concentration. So this first filter is going to highlight those grains that have 204 concentrations that are higher than 600 counts per second. Then the second filter here is the precision filter for the 6-8 uncertainty. So this is going to be, as these comment says, is the maximum acceptable error in percent in the 206 to 38 age. So if you go to your U and V columns, you'll see that U contains the 6-8 age of that particular grain, and V contains the 1 sigma error on that age. So if there are any grains that have uncertainty that is more than what we've set in this threshold, so greater than 10% of the age, then those analyses are going to get rejected by HCalc, and they're going to be filtered out and highlighted in blue. Likewise, if you go to cell J1, here is where you want to type the maximum acceptable value for your 206, 207 uncertainty. So as the comment says, this is the maximum acceptable error in percent, just as we looked at the 6-8 error. And then that's going to be here, you'll see it in the X column. This is the uncertainty. And if you look at your age, 6-7 age, that is just right to the left in column W, if there's anything that is greater or any of these uncertainties are greater than 10%, then those are also going to be discarded due to this filter. The other filters that we're going to have to play with a little bit further as we look at your data set in particular are the discordance filters. So we typically have set a threshold for 5% reverse discordance. So anything that is more than 5% reverse discordance is going to get highlighted and discarded. We usually have 20% discordance filter for normal discordance, but as we go further into your data set, you'll be able to see that we can tweak this a little bit depending on your particular data. Okay, so now what we're going to do is we're going to go down this AA column looking at those analyses that are highlighted in blue and that have some comment in here. And this comment is going to tell us which one of the filters is the one that is responsible for having this grain rejected from the data set, or why is it flagged. So some of these, for example, this is reverse discordance. We see that the 6-7 age is significantly younger than the 6-8 age, and there's nothing we can do about this one, and start going down. There's one here that is discordant. It has a significantly large uncertainty in the 6-8 as well. Down here, most of these grains, you can see that a lot of them have high 204 values. So if you look at these, the 204 counts per second that we actually got from those grains, they're usually not higher than 1200 or 1500. So in this case, in this particular sample, and this depends on what sample you're analyzing, we have this threshold set to a relatively low value because oftentimes we're looking at very young grains. So for a young grain, a higher common lead content has a greater impact on the age. But as you go older, then the 204 correction has a smaller and smaller impact. So for example, in this particular sample, a lot of these grains are really old. So if you look at grains that were discarded because of high 204s, they're close to 1600 MA, 1500 MA, and a lot of these ages in the Precambrians. So in this case, we should be able to flex this threshold a little bit. So I'm just going to go ahead and change this to 1200, and you'll be able to see that as I change this and then hit order, a lot of these grains that were highlighted in blue are either not going to be highlighted anymore or are going to be just filtered out by some of the other thresholds that we've set if they violate some of the maximum uncertainty filters. So I'm going to go ahead and click order and scroll down again to that part that had a lot of high 204 grains, and you can see from column AA that a lot of those high 204s are gone. So now, for example, if you look at this grain, number 41, it was discarded before because it had a higher than 600 counts per second 204. It has 863, but now that one is being included because it doesn't violate any of the other filters. Okay, so as you'll see now, a lot of these grains are just being rejected because they are normally discordant. And in some cases that's fine, depending on what the objectives are that you have. If you're after a very precise and very accurate age of a particular population, you don't want to introduce any noise by including grains that have high discordance. But if what you're after is the complete story of provenance, sometimes you can bias your data set if you selectively exclude some of those discordant grains, and we'll discuss that in another video when we talk about the interpretation of detrital zircon samples. So okay, we just finish going down this column. A few more are being discarded because of this high 204. I'm just not going to go above that new threshold of 1200 counts per second. And actually, none of these samples are being rejected because of the maximum uncertainty thresholds that we set for the 6-8 age or 6-7 age, and that's good news. That means that all analyses are more precise than 10%. So this was a good run. Okay, so I want to hit order again, so everything's fresh, and now we have our data is basically ready to be exported to a data table. So all that you want to do is just scroll a little bit here to the right until you see this button that's called Zircon Data Table that is close to column AG. Click on it, and then the macro is gonna export this final data table that you can include in your publications down here in the tab that's called Data Table. When you go to this data table, you'll see that you have the isotopic ratios in columns G through K that you're gonna need to plot your Concordia diagrams. And in columns L through Q, you have all the different apparent ages of the three different isotopic ratios that you can use to calculate an age in the uranium lead system. So here in column L, you have the 206 to 38 age, and column M is the plus or minus at 1 sigma level. And columns N and O, you have the 207 to 35 age with its plus or minus, and column P has the 206 to 07 age and it's plus or minus. And then here to the right, you'll see that you have another two columns that are called best age. So what best age means is that, depending on where you are in the geological timescale, there's going to be one of these apparent ages that is going to be better for estimating what the real crystallization age of your sample. As you know from previous videos where we explained a little bit the systematics of uranium lead, if you are working with young samples that are younger than roughly 1 billion years, then your 206 to 238 age is probably the most precise and most accurate estimate that you can make on the age of a grain. But if you're way back in the Precambrian, so anything that is older than 1.4 GA, so anything in the Meso and Paleoproterozoic and things like that, the most precise ratio that you can measure is the 206-207 ratio. And in addition to that, if a grain has been affected by modern lead loss, then that modern lead loss is going to significantly affect the 206-238 and 207-235 ratios, but it's not going to strongly affect the 206-207 ratio. So it's not only the most precise, but the most accurate approximation of the real age of that grain. So there's going to be a threshold too. There's going to be an age that divides when we're going to consider the 206-238 age to be the best age for a particular grain, and when the 206-207 age is going to be considered the best age. To look at an example, let's look at this grain number 1, where you have a 6-8 apparent age of 1221, you have an apparent 6-7 age of 1235, and then what's shown here in the best age column is 1235. So there's a column that I'll show you here in a minute where you can set that boundary. When do you start considering the best age to be the 6-7 age instead of the 206-238 age? So that's going to change from sample to sample. We normally, if you go to sheet 1 and go to cell S1, then in the comment, so you'll see that this is the cutoff for 206-238 versus 206-207 ages that are used as best age. So this value is generally between 800 MA and 1200 MA, but we allow the user to flex it a little bit. It is going to be very common that in a lot of samples you're going to find a big peak right around the age of the Grenville orogeny, that is 1 GA. So one thing that you don't want to do is just set this parameter just right in the middle of a population, because what can happen is you can artificially generate two peaks, one by having half of that population use the 206-238 age as the best age, and the other half use the 206-207 age as the best age. So what we want to do then is just to evaluate our data, this particular data set, and see what kinds of ages we have and where we want to set this parameter. Okay, so in order to set the right threshold for the age cutoff, we're going to use isoplots. So we'll go to data table, and then you're going to highlight all the grains that you've analyzed. Right? You can go up here to the upper ribbon and just click on the isoplot icon. This is going to open this window. So what we want to plot is we want to go to this drop-down menu and select a probability density plot. Our input errors are 1 sigma and absolute, and then you're just going to hit OK. It doesn't really matter what you select here. You can click OK again. We just want to take a really quick look at the data. Okay, so what you can see from this plot is that there aren't many grains that are around that age, that is the threshold around 900 MA. But there's this one grain, so there's nothing at around 800. So the safe way to go would be to go back to sheet 1, and on that threshold, that cutoff set 800, and then hit order again. So when you change something in this sheet 1 tab and then hit order, it's going to get refreshed in the sheet 1 tab, but it's not going to get refreshed in the data table. So now an important thing to remember is that every time that you change one of these parameters and you hit order, then now you also want to click on the zircon data table again. So it's going to export all those values back to the data table, and that's going to represent the changes that you just made. Every time that you hit order and then recalculate some of these values and reapply some of these filtering thresholds. Okay, so the last parameters that I want to show you how to interpret, if you go back to sheet 1, you'll find these three on columns T, U, and W that we have not talked about yet. So if you look at the comment that is here in column T, it says that is the cutoff for the Concordance filter and 6-7 precision filter. So what this filter means is that any ages that are below this value are not going to be filtered out by the precision on the 6-7 ratios, right? Because we know now that as you go younger, those uncertainties and the measurements are larger. And also, the discordance filters are not going to be applied. So in general, we usually have this factor just being between 600 MA and 400 MA. And then depending on how your data looks and what analyses are being rejected on column AA, you can modify that. So the other two values here, and these are cells U1 and W1, are the systematic errors on the reproducibility of your standards. So these two values that you'll find here in cells U1 and W1, they represent the 2 sigma systematic error on the measurement of the 6-8H for U and the 6-7H for W. So when you're measuring any ages on the laser ablation ICPMS mass spectrometry, you have several sources of error. One source of error is just the analytical uncertainty that is attached to the measurement of a single grain. But then there are also some other external factors that generate a systematic error. So the total uncertainty is the propagation of all these errors that are involved. So these errors up here tell you what the systematic error for that particular run was in each one of these two ratios. So at the end, in order to calculate any final age, what you want to do is you want to propagate your analytical uncertainties with these systematic uncertainties. And remember, these uncertainties up here are given in percent, and this is a 2 sigma level. So now that you've looked at all these parameters, last thing that you want to do is just click order again, click zircon data table. So what you have here on your data table tab reflects all the changes that you've made to your reduction. Sometimes you got to be careful because if you analyze some secondary standards, it could be R33s or Duluth-Gabbro zircons or whatever. You want to go down this column A and make sure that you remove those from your plots, because otherwise you're going to be incorporating some ages that are not part of your sample. In this case, we don't have any, so we don't have to worry about that. All right, so now that we have our final data table, we're going to make the final plots. So these green columns here over in the data table tab contain the isotopic ratios and the error correlation factor that you need to plot your Concordia diagrams. And then the columns that are highlighted in yellow are the ones that you're going to be using for your probability density plot. So in order to do this, we're going to use isoplot again. So you want to take the columns that you want to plot, just highlight them all. Right. So you go here to the upper ribbon and click on the isoplot icon again. It opens isoplot, and in this case, isoplot already identified that you're going to plot a uranium-lead Concordia. The input errors in this case are 1 sigma, and they are in percent. So we want to plot, and we don't want to calculate because this is a detrital sample, so we're going to have several different age populations, and it's not a single age that we can calculate. I usually untick the filled so you can see ellipses more clearly. So we're going to have red error ellipses, and this is going to be plotted in normal Concordia space, that is the Wetterell type Concordia. So you just click on OK. It's going to ask you how you want that curve, if you want a band that reflects the decay constant, or you just want a line, and if you how you want the labels. So I usually just do a line with the horizontal labels, click OK. It's going to take a few seconds, and then it's going to generate a publication quality Concordia diagram. So this is these diagrams are scaled to accommodate all the data that you've highlighted. But say, okay, I'm not interested in just looking at the whole spectrum, but I only want to focus on these grains that are between 1 GA and 1400 MA. So that's the area of my interest. So you can go back to data table. You go here to the isoplot icon again, 1 sigma percent, and then you want to untick the out of scale option. Click OK, and then you'll set your minimum age, whatever you wanted, 1000 MA, and maximum age for 1400 MA. So you want to have the age ticks as small circles with horizontal labels, then click OK, and now the program is going to do a Concordia that is zoomed in into the area of interest. So now you can have the resolution, whatever resolution that you want for your Concordia diagrams, and focus on specific areas to look at different clusters. Okay, so last of all, to make a probability density plot, you want to highlight all the cells that are in yellow, then go back to your isoplot icon. And now here, the plot type, you're going to select probability density plot. The input errors are 1 sigma and absolute in this case. So remember that for the Concordia diagram, the input errors are in percent. But here now, for the best age, the uncertainties are in absolute values. So you click OK. And over here, the x-axis label, you can type whatever you want, but this is the age in millions of years. You can tick and untick this include histogram, so on top of the probability density function, it'll include or not a histogram, and for that histogram, you can make the plot, the rectangles being filled or not filled. You can select, bins starting at 0 MA, and then the width of each one of those individual bins. You can set it to whatever value better fits your data. You can do 20. Okay, and now it's going to take a couple seconds, and it's going to generate a publication quality probability density function. So again, say that you want to focus again in this same area where we focused our Concordia plot, that is 1 GA through 1.4 GA. So you can do it here too, is just go to the x-axis, double click on the x-axis, and go to scale and change the minimum scale to 1000, maximum scale to 1400. Click OK. So you'll see that it modified the probability density function, but it didn't rescale the filled histogram. So in order to fix that, you just go up here to the upper ribbon where it says, where it has the link to isoplot, and you do format chart symbols and rescale filled symbols. So it'll rescale it to the values that you have now on your x-axis. So one last thing to note here, when you're working on making the final plots that you're going to take to another program and edit them to make the final figures for your publication, is that you got to realize that when you do a probability density plot that does not have a histogram that is filled, and I'm going to do one here right now. So probability density plot, this is not going to be filled. So this one has, if you rescale it again, has no problem rescaling the histogram bars. And so you don't have to worry about rescaling the filled symbols. But on the other hand, depending on what version of either Adobe Illustrator or CorelDRAW you're using, filled histograms or unfilled histograms are going to be easier to handle. So you want to find that out first before you make all your plots, and then just generate your plots in a way that is going to be easier for you to handle when you're doing the final edits to your figures. Okay, so now you have all your data. It's all final, and you're ready to do the plots, ready to start jumping into interpretation and writing your manuscript. But before we finish this, I just want to show you some of the other plots that we have here that might be useful in some cases. So there's a plot of age versus uranium concentration. And sometimes, so in some igneous samples, you'll see that there are trends of decreasing best age versus uranium concentration. And what that means is that in some of these grains, it might be that they have accumulated enough radiation damage such that the age is being affected by lead loss in the high uranium concentration grains. So then, if that was the case, you want to put more weight into the low uranium concentration grains that are less metamictized and therefore are going to be more retentive to your radiogenic lead. This next plot, uranium thorium ratios versus age. So uranium thorium here on the x-axis versus age on the y-axis. So uranium thorium is commonly used as indicator of what the origin of a grain is, whether it is igneous or if it is metamorphic. So for the most part, people agree that values that are significantly higher than 10 in uranium thorium ratio, or that are lower than 0.1 if you're looking at shrimp analysis, because you're looking at thorium uranium ratios, those grains are commonly considered as being metamorphic in origin. But in this case, all the grains cluster are really low uranium thorium ratios. meaning that they have high thorium contents and are likely of igneous origin. You can just look at your age versus concordance, and then you can see some trends here of how concordance decreases as your best age decreases as well. And these are trends of lead loss that are not modern lead loss events because they're affecting the best age, that is the 6-7 age. So that's one thing to note. You know that if there is a modern lead loss event, your 6-7 age is not going to be affected significantly. But if lead loss is not modern but occurred at some time in the geological past, say some of these grains that are 1500 MA old suffered a metamorphic event that generated lead loss at 500 million years ago, then that is going to modify your 6-7 ratios. Last things to look, you can take a look at your Concordia plot here in normal space, or you can take a look at the Concordia plot in logarithmic space, and then you'll see that most of your grains are lying on top of Concordia really nicely. And that should be it. Now you have your final data table. It's all reduced. Now you just want to make sure you go to File, save this thing as, go to your folder or any other folder where you want to save it, and then this is sample 11 MIAR 09, and you save it with that name, and that's it. This is how you reduce a detrital zircon sample using NuPM HCalc. And coming up next on Beam Team TV, we're going to take you through the thrills and spills of reducing your own igneous samples through HCalc.